You're going to completely fill out Table 1. You're going to get the original pendulum length for each run in meters, the masses that you choose in kilograms. These capital H values are the equilibrium heights measured from the bottom of the dotted line when the pendulum is hanging straight down to the line across the middle of the pendulum bob. You get your two angles measured in degrees. At each of those angles, you will measure additional heights for the given length. The subscript 1 here refer to the first pendulum length, and then for each of those two angles, so subscript 1 and 2. The same is true for the second pair of small h values and their subscripts, referring this time to the second length and each of the two angles. You're going to swing the pendulum. There is a period counter on the simulation, and it will calculate the period for you. You should be able to get the periods for both of your angles that you choose, each of the masses of the pendulum bob, and for each length. Make sure to record the correct pendulum period for the correct collection of pendulum properties. For example, line 1 would be the period for the original equilibrium height, capital H1, brought to the first angle and its new height, small h11, with a mass m1 of the bob. The remaining columns in Table 2 are the calculations that are to be done from the data. If you do these in Excel, as I will illustrate shortly, then you can simply copy the corresponding tables from your Excel sheet into the calculations portion of your lab write-up. You will not have to fill in these blank table values in that case. The derivation of a relationship between the final linear velocity and the angle the pendulum is extended, the period of that pendulum, and the length of the pendulum begins by considering an arc. Your initial angular velocity is here, and because you're at the top of the path, its value is 0. Your final angular velocity is at the bottom of the path. You know your angle in radians, and you know the time to go from here to here. That is 1 period. So with that in mind, how much of that time of that period is taken from going from here to here? You will need that as part of your proof. You will find in our text a set of rotational kinematic equations. 2 of them contain omega final and omega initial, and you need omega final. You want to combine these 2 equations so that you can get rid of alpha, the angular acceleration, which you do not know. Do not forget that the initial angular velocity is 0, which will make the equations even simpler to manipulate to eliminate the angular acceleration alpha. Once you have an expression for the final angular velocity, do not forget that the time is related to a fraction of the period, which will let you build the period into the expression. The last step will be to convert your final angular velocity into a final linear velocity, remembering that the radius is the length of the pendulum. That expression of the final velocity as it relates to angle, the period, and the length of the pendulum are what you will use to calculate the final velocities, either by hand or by putting the expression in Excel. This is my version of Excel for this lab. I have set it up so the periods are all listed here in column A, rows 2 through 9. My heights and masses are listed below the labels in row 2. My angles are listed in column J, rows 2 through 9, like the periods. You should make sure you match the angle with the appropriate period as you go down this column. Row K is needed because when it comes to calculations, Excel needs the angles in radians and not degrees. You will need to put a calculation in these cells to do that conversion. Column L is where I put my lengths. Again, make sure to match up the proper length with the proper period and angle. The remaining columns are the calculations that are to be performed. These are the columns that would be copied into your Word document as a calculations page if you choose to do your calculations this way. So, for example, here's my calculation of the final velocity. It is pulling in information from the period, the angle in radians, and of a length. The second one is set up in the same way, the third one the same way. I then squared my velocities. You do not have to have a square velocity column. You can go on and just do the calculation of kinetic energy. But I just wanted to make sure I was doing everything right. The squared column is simply squaring the previous column cells, m2 squared for this one, etc. Kinetic energy is 1/2 the product of the mass and the square of the velocity. Make sure you grab the right mass when you are combining it with a velocity. In my case, I am simply pulling from the velocity squared column to complete my calculation. If you choose to do your velocity squared here, make sure you're matching the correct mass to the correct velocity. The potential energy is equal to the product of the mass, acceleration due to gravity, and the difference between your capital H and your small h values. For example, it is B minus D. So I just took the bigger minus smaller. I did it this way so I did not have to worry about signs. Again, make sure as you're going down this column that you're matching the correct mass to the correct difference in heights. The last column that I have listed is a ratio of kinetic energy and potential energy. The closer that number is to 1, the closer your data verifies the conservation of energy, since you are going from total potential energy, initially, to a final kinetic energy at the bottom of the path. If it is not close to 1, then you should go back and make sure that you did the right calculations. That is, make sure the correct masses are multiplied by either the correct square of the final velocities or the proper differences in height. Do not forget to provide example calculations for each of the columns of calculations that you are asked to provide. This is true if you do the calculations by hand or using Excel. So once you have completed the proof, you should put in one set of your data to get a final velocity. This would then be the first value that you put in the provided data tables if you're doing calculations by hand, or the first cell value in your Excel spreadsheet of final velocities. There should be one example of a kinetic energy calculation with your data, again, listed as the first kinetic energy column in the data table or your Excel spreadsheet column of kinetic energy values, and one example of the gravitational potential energy with your data and its placement as above. If you choose, you can also show an example of the calculation of the ratio of kinetic and gravitational potential energy. This lab is all about calculations. There are no graphs. So the points for this lab are mostly concentrated in the calculations, and credit is given for those done properly. There are sample calculations that you are to perform. If you do it by hand, then the subsequent calculations with those equations are to be put in Table 2. If you do the calculations with the help of Excel, the sample equation should appear first, followed by the table of calculations copied from Excel. To make this copy table clearer, highlight those cells that you are going to copy, including the column labels. Go to the font section where you will see a small grid box. Click on it. In the drop-down menu, click on the option All Borders. The grid you highlighted should now have borders all around it. When you copy it into the Word document, it should be clearer to read. Make sure to include the completed data tables and the questions. Save your Word document and submit it to Blackboard.